I now call to order the 2297th meeting of the Philosophical Society of Washington in the 141st year of its founding in 1871. Good evening. My name is Lloyd Mitchell, and I'm the Vice President of the Society. Thank you, Larry. The oldest scientific society in Washington, D.C. The members of the Society are committed to providing a forum for discussions of the scientific topics of the day of interest to all educated men and women. On behalf of President John Ingersoll, who's unable to join with us this evening, we welcome our members and guests to this evening's lecture by Marwan Hassan, Professor of Geography at the University of British Columbia. He will be speaking on River Valley landscape evolution. The lecture this evening is sponsored by our member Paul Rich and the Policy Studies Organization in cooperation with the American Public University. And thank you, Paul. Tonight we are delighted to have as our speaker Marwan Hassan, Professor of Geography at the University of British Columbia. Dr. Hassan will tell us about sand stories, the stories of fish, floods, and folks in the history and evolution of river valleys. We will learn how river basins are dynamic and complex systems shaped by multiple active geomorphic processes such as climate and tectonic activity. We'll hear about the interactions of these processes and their effects throughout the historical record. In particular, Dr. Hassan will discuss sediment dynamics along the Yellow, Yangtze, and Mississippi River basins and the effects of contemporary land use practices. Marwan Hassan earned his PhD in hydrology from the Hebrew University of Jerusalem and is an expert in water and sediment routing in watersheds and modeling the evolution of channel morphology. His research projects include landscape evolution, the role of river systems in aquatic habitats, sediment dynamics, water resources and management, urban hydrology, and water quality. And Dr. Hassan?
Thank you. First, I would like to thank the Middle East Dialogue for inviting me to talk here today. And I also thank the Philosophical Society of Washington for also inviting me to talk. In the morning, I talk about water in the Middle East, and specifically I talked about the Israeli-Palestinian context in terms of water. And my points were that there is enough water for both nations and there is no really reason for war over water, although you hear that all of the time in the news that water-related wars are actually a reality in the Middle East. The other thing that I did, I link it also to the human rights issues and the right for water, which is based on the Declaration of the United Nations. Then I went and I spoke a little bit about the Nile River, and I showed how the Nile River moved from conflict to cooperation, which is the Israelis and the Palestinians can learn from that. So as a Palestinian myself, I really feel honored to be here. And I'm happy that they invited me to come here, and I hope that more Palestinians will be invited to talk and to promote dialogue with the people from not only North America, but around the world. What I will do today, I will talk a little bit about the Middle East, but in a different way, but I will talk about the globe, because what I'm going to do is to talk about stories of sand. And the way that I see the landscape that you see in front of you in a way of sediment movement. The picture in front of you, it's taken from the west coast of Vancouver Island. One of my study sites is just here in this area here. What you don't see the extent of logging that happens in this landscape, but what you see a landscape that evolved and developed over a very long period of time. And the question how this landscape looks the way that it looks. If I ignore for the moment the climate and the geology in terms of tectonics and lithology and focus the prime kind of process that changed the landscape, which is the sediment transport, then I can try to explain what sort of differences we find on the global scale. So the landscape in front of you, it could be very similar to a landscape in a desert in the Middle East or anywhere in the world. The difference here is that this landscape is covered with vegetation. So the vegetation play a major role in shaping these landscapes. But in terms of a process and in terms of physics, it's all of it the same. So all of what we do, we change the hydrological cycle and we change the coverage of the surface, and the process are the same. So I'm going to go through processes from the Middle East into Europe, into North America, China, and so on all over the globe to emphasize a certain kind of ideas. Okay, one of the major issues if we look on the history and if we read the historical kind of accounts with soil and soil erosion, and also we look on archaeological sites, we come to the conclusion that civilizations developed around a certain kind of agricultural activities, and they declined due to soil erosion or due to salinization of the land, which is becoming not useful for agricultural land. Mesopotamia is a very good example for that. All of the city-states in Mesopotamia, they kept shifting from one place to another as a result of soil erosion and desalinization and so on. And the speculation is that empires and civilization survives roughly about 400 or 500 years, and they decline. And one of the reasons, it's not just politics, but it's also one of the reasons for the decline of civilizations. It has to do with soil erosion and environmental degradation. If you look at the diagram in front of you here, this is a picture from Petra in Jordan, which used to control all of the trade routes from Arabia into the eastern part of the Mediterranean, survived for 400 or 500 years, and it declined. And the evidence shows that environmental degradation was a key issue of the decline, in addition to shift in the trade routes. In the case of Egypt, the picture is more complex due to the fact that the Nile kept actually flooding the area around for agriculture and kept bringing a fresh sediment that keep kind of fertilizing the soil. And based on that, Egypt civilization survived for quite a lot of years, very long years, probably the most surviving civilization on earth, due to the flooding of the Nile. The building of the Aswan Dam led to a situation that Egypt started using chemical fertilizers, which now Egypt is the largest per capita users of chemical fertilizer, which led to a major degradation of the land use and of the quality of the land, which could actually explain some of the environmental issues that Egypt faced and so on. So there is a link between the soil erosion and societies. And this phrase and picture actually tells all of the story that why we should worry about soil erosion and salinization. This is the most powerful statement that I actually read, that a nation that destroys its soil destroys itself, which is true. And you see that the American civilization, the North America and so on, went through a tough period in the 1930s, and these pictures are actually an evidence for that. So there is a link between soil degradation, erosion, and so on civilization. So what I will do today, I will actually go over three kind of different processes that shape the landscape. These processes sometimes help each other, sometimes compete with each other. Sometimes they dominate the landscape, sometimes less, and so on. The first one, which is a little bit technical kind of topic, which is related to my fundamental research on the control of the sediment transport in the stream, how sediment move, what control the sediment movement, what sort of things we do in order to model and to estimate sediment transport. So I will start with this. It's a little bit technical, but I will do my best to explain it in the easiest possible way. Then I move and compare fish and how fish, sockeye salmon, Chinook salmon, how they modify the landscape, how much sediment fish can mobilize to compare with a flood. which is more stronger, fish or floods, in terms of shaping the landscapes in fish-bearing habitat and the streams. When I finish that, I will move on to the humans and how humans actually modify the landscapes and how humans actually dictate what's happening. The notion in the end that really very hard or very difficult to find these days, what we call it a natural landscape with no human intervention, a topic that hasn't been studied that much. So I will look on these kind of three kind of agents of shaping the landscape, that they compete with each other, but sometimes also aid each other and help each other to shape the landscape. So the first question has to do what control the sediment transport in streams and why we should worry about sediment transport in streams. Well, of course, landscape evolution and explaining the landscape that we see in front of us is the key issue, but it has to do with the human functions and building bridges, dams, and so on. All of these are important to consider. If we look on the process itself, and this is a kind of a summary diagram that looks on it in terms of input to the system. In any river system, we have water. Without water, nothing occurs in the landscape. So the major issue is water. Then we have fine sediment, which is very important for fish habitat, as we'll see later on. Increase in the fine sediment could degrade the habitat. We have the coarse sediment, which is responsible for the growth of diatom, algae, and so on, which enter to the food chains of the fish. And then we have wood, which is very important kind of part of the channel system in forested areas. In terms of processes, we look on the sediment transport, which will be the focus here. The bank erosion is a source of sediment in the system, but also the floodplain can be a source of sediment. And these together makes what we call it the channel morphology, which is the bars, pools, riffles that I will be using later on, and the floodplain, which I will not touch that much today. And then all of this will dictate the habitat that we find, which is the spawning habitat, the quality of gravels, the rearing habitat, summer, winter, and so on, and the floodplain habitat, which will affect the salmon. So I will start by looking on this, then move to this here, link them together, then move to a human impact on the landscape. So I will be coming back to this kind of diagram. One of the easiest way to estimate sediment transport, and in terms of physics, the problem is really easy to deal with it. We know the forces that act on grains in the channel, and one can do a simple calculation of how much sediment move. This will save us a lot of money because we don't need to go to the field and to spend a lot of time and effort in order to collect samples and so on. So the motivation here for what I'm doing is this diagram that you see in front of you. These data from Casper Creek. It took a lot of effort for the forest services in the US to get these data. And in comparison, this is one of the functions or one of the models that you see here. And this is the most recent model. I could plot any model I want, and I show you roughly the same results. The conclusion here is that the predicted value is usually 2 to 3 order magnitude larger than the measured value, which means that you go to the people and tell them that you have a 0 sediment transport or a 3 order of magnitude more than that. And you cannot kind of plan your activity within the basins based on these numbers. You need really real numbers. You need to know if the dam will survive 50 years or 150 years or 500 years, which is very important for this. So the motivation and the deviation from looking on diagram is the fact that we cannot use the theory in order to predict, and I will explain why soon. So if you look on rivers are very complex system. They are complex because we have irregular boundary. It's made of wide range of particle sizes, as you can see in the front of you, different particle shapes and different surface organization, the stones touching each other and so on. So we have a very wide range of organization in the bed itself, which makes it very difficult to describe. On the top of that, we have a turbulent flow. And between these two issues, it's really very difficult to describe the boundary and to develop a reliable sediment transport models. And this is why the model that you saw before, it did not predict the sediment transport in streams. So what I'm going to do here is to look on why difficult to predict. This is one of the diagrams that I will use first, which is related to the particle size. In this part here, you see quite large bars in the channel itself. This is Carnation Creek in Vancouver Island. You see sand on the surface. You see wide range of particle sizes, but you see a completely different bed than the one that you see here. This is another river. You see quite a lot of organization, arrangement at the surface itself, which increase the stability of the channel, decrease the sediment transport. And if we compare this with the Schmidt line in Germany, you see the kind of beautiful structures on the surface that they act as a group rather than one particle size, because the theory deal with them as individuals, while in reality they act as a group of stones and increase the stability of the system quite significantly. And here, as you can see, another type of situation. So we have wide particle sizes. We have a range of surface structures. These are very wide, which makes it very difficult to describe. And if you look on the surface of one of these streams, you see these kind of transverse features that actually very important in terms of resistance, increasing the stability of the system, which means decreasing the sediment transport rate. And when you trace all of these things, you kind of come to a net of structures, cells, and so on that cover the whole landscape, which means they decrease and increase the velocity of the water, and this way they increase the stability. What you see here in front of you is one of the most stable kind of environment versus the one that we saw before. As I will explain later on, it's considered to be less stable. So rivers tend to develop surface structures that they are actually designed to reduce the sediment transport rate. And the second point here to make is that the model doesn't include what we see here in front of us. These are two different streams, one in the desert and one in humid areas or snow melting system. In the desert, what you see is stones kind of floating within a sand. There is no differentiation or real differentiation between the surface and the subsurface. You see a mixture of sediment with no sorting, vertical sorting I mean here in terms of particle size, versus in a humid snow melting system, you see a coarse layer on the surface, and beneath that we have a fine kind of layer. What happens is that the smaller grains infiltrate between the larger grains and go underneath the surface, and this is the way they are protected. So in humid areas, we find what we call it armored layer, which is the coarse layer in the surface, which is with the structure that I showed before, increase the stability of the system and decrease the sediment transport, which is one of the things needed for the habitat, the fish itself, because it doesn't need a lot of sediment transport. In the desert, we don't have the same conditions. As you can see here, these particles are floating in the surface, no segregation between the surface and the subsurface, which means that in desert we have a completely different hydrological sediment supply regimes than in humid areas. What I'm going to do is to explore the structures that I showed before and the armoring or the coarsening of the surface in comparison to the surface by looking on experimental work, field work, experimental work, and theoretical work. And if I take these two cases that you see in front of you and translate to a figure, what I see, this is the particle size distribution of the surface. This is 100%, and this is particle size. You can see the same here. This is the particle size in millimeters, and this is 100%. And in general, what you see here is that the surface here is much coarser than the subsurface. This is the subsurface, the fine material, and this is the surface, which is about 3 times, if I look on the median size, coarser than the subsurface. If I look on the desert stream, the two lines on the top of each other, which means that hydrologically and geomorphologically, these are two different systems as we see here. And it has a lot of implication to water resources and habitat issues. Okay, so what I want to do is to start by looking on the sediment supply, and this is really a major issue. The United States spends about $3 billion a year and more in river restoration, and one of the key ideas behind river restoration is to supply gravels to rivers, because these rivers starve from sediment because of dams and so on. So the idea is that you supply the gravel that these that fish, salmon and so on need. And this is the kind of diagram that you see in front of you in California. So the question is that how the sediment supply is likely to change the surface, and this is a key issue. And I did not see that much study done on this issue in the US in relation to the sediment supply. So what I'm going to do is to look on the sediment supply. So now remember, this is system, low sediment supply, as I said before, well-structured surface, a blank kind of surface, very little features in it. This is armored, coarse surface. And this is the second feature, although it's in Vancouver Island, not desert, but it's similar to a desert system. High sediment supply, bars completely different, no surface structure, you don't see these transfer features, and not armor surface, you can see a lot of sand. And what I'm going to do is to look through evidence in the field first, and then go into experimental work. And this is the field evidence. What we have here, just I plot the median size of the surface versus the median size of the subsurface. And what I will look first on this diagram here in this side. 1, it means that the surface and the subsurface are the same. 2, it means that the surface is twice larger than the subsurface. And 6, and so on. And my hypothesis here is that in a low sediment supply system, which means starving conditions, this will lead to a development of coarse surface, as you can see here. As the sediment supply increase, I move it from a well-structured, stable channel into a highly mobile channel, as you can see here. And this is what I'm going to do. I'm going to look on how can I create these conditions versus how I can create these conditions. I will come back to this here, which is related to the hydrological regime later on. Okay, I did this as experimental work in one of my laboratories, as you can see here, a scaling model and so on. And here what I compare between the zero feed, which means that no sediment supply into the system. And what you see here, this is the particle size distribution of what moved versus the particle size of the surface. And you see a shift over time from 8 hours to 96 hours, from a little bit kind of coarser surface to much coarser surface, which means that as we reduce the sediment supply, or as we stop the sediment supply, which what happened immediately downstream of the dams, we increase significantly the particle size on the surface, and this leads to increase significantly the stability of the surface. If we supply sediment, and what you need to think about it here, that 0 here is this case, we increase it by 50% here from the normal conditions, and 100% is the one normal conditions. And this is what we see in zero feed or no feed. As we increase the feed, we shift from very coarse surface into a finer surface. And what you can see here, with the mixture that we start in, we end up in, which means that our hypothesis is correct, and which means that when we supply sediment to restore habitat, we need to take into consideration that we shift the system from a coarse surface stable bed into more mobile bed. That it means that implies that we need to supply all of the time sediment for the system to keep moving sediment, and this is what required for habitat. So the idea to go in and to supply sediment once in a while, this is what they have been doing in many places in the US, it doesn't work. It worked for 2-3 years. In order for the system really to function, you need to keep supplying sediment all of the time and keep shifting the system from here to here. If the system is here, then it's becoming really coarse, too difficult for the fish to use, and this is one of the major issues with the habitat, as I will be talking about later on. Now, if I move and look on it in different way, I can play with what I can feed, because this is the nice thing with experimental work. I can dictate what the supply. Now, if I want to maximize the activity within the system, or I want to maximize the sediment transport rate, all of what I need actually to do is to feed sand. This is the transport rate, and this is the feed rate, and this is the equilibrium condition. This is the 1-1 line. So if I feed what move, I end up around the equilibrium conditions. But if I want to enhance the mobility of the sediment for certain reason, then I need really to feed sand. Sand increase the space between the grains, reduce the resistance, increase the velocity of the water as a result of reduction in the resistance, and this lead to more mobility. If I want to increase the stability of the system, I should supply coarser material, as you can see here. And this is very important for restoration, which needed to be taken into consideration with other factors, as I will explain later on. Okay, now how the flood actually act. What you see here, this is a hydrograph in deserts, which means that it's a dry bed here. And this is a flood front that's coming, and I'm running in front of it. My assistant, instead of helping me to escape the flood, he ran to get pictures. So as you can see here, I had to struggle and to move in front of a kind of wall of water coming down the streams from Jerusalem into the direction of the Dead Sea. And the bed, after a few hours, become like this again, dry, which means that the flood goes up flashy and down quite fast. And this is why we think it doesn't develop armoring or structuring in the surface. These two pictures taken from a river, Elbow River in Alberta, and what you can see under normal flow conditions, snow melting system, we have low flow here that keep actually mobilizing the fine sediment versus high flows that shape a lot of the landscape. So we are looking and comparing these together. Again, I'm going back to my field, because my field is kind of my compass. I keep kind of getting ideas and compare with it. I compare in the beginning the low and the high sediment supply, and I move it from structure to non-structured surface. Now what I am going to say that in a flash flood system, there is no time for the system to sort sediment. So the sediment will deposit exactly the way that it moves in the river system. And this has implication toward restructuring of all the floods in desert stream. Versus in a snow melting humid areas, there is enough time in the flow to sort sediment, and we will develop this kind of structured armored surface. To answer this question, again, I use the same kind of experimental method, but what I did here, I compare different hydrograph shapes. This is a discharge that roughly we can expect from snow melting, although this is constant, but in a snow melting system, it's increased very little over a very long period of time, and it goes back to the same situation. So it's roughly almost constant flow. In desert stream, we might find something like this, which is a long kind of falling part of the hydrograph, as you can see here. But in the most flashy desert of the Middle East, we have a quick rise from zero, actually, up to very high flows within 10 minutes or less, and a very kind of fast falling limb, which is within 2 hours, event can come and disappear, which is a completely different hydrological regime. This will develop armor structure surface. This will not develop armor structure surface. Again, experimental work in order to solve this issue. And my assumption here is very important, really, is that the surface of the channel itself will keep it changing as I'm going from low flow to high flow till I reach the peak. The sorting will happen when the flow starts declining, because as the flow keep going up and up, the surfaces keep adjusting to the new flow conditions. As the flow decline, then we start getting some sorting. And so my idea is that the longer the falling limb of the hydrograph, the more sorting we will find. The one extreme is the snow melting system, which is very long, versus the other extreme, the desert, which is very short and there is no time. So this is a kind of simplifying of the model that we develop for that by looking on the time for the hydrograph, for the time for the sorting, and the ratio between them. If it's much, much higher than 1, then we have sorting armoring, which is a snow melting humid systems, versus arid system when we have this ratio is much, much less than 1, as I will show. The same kind of method we used, and this is what we get. This is the constant snow melting system. We have, again, the particle size distribution. I decided to use all of them the same kind of results, some kind of figures to show different results. So it's easy to follow. This is 100%. This is particle size. This is C, similar to it's at the logarithmic kind of a scale for the particle size, but the particle size increased that way. That's simple. So again, in the constant flow here, we find very well armored surface, exactly what we get from snow melting system. We have a little bit of armoring here because of the hydrograph is very long. It's about 10 hours, 8 hours, as you can see here. And the shortest kind of flashy desert kind of hydrograph end up exactly what we want, which means that there is no armoring and the system remains the same. Again, if I compare the flashiness of the hydrograph, this is a flashy quite up and down within less than an hour in our experiment. It's exactly the same. If we increase the length of the hydrograph falling part, this is becoming clearly armored and armored. Okay, the key actually, and our actually assumption is correct, that the sorting happened in this, and the key here is the length of the falling limb of the hydrograph, which is very short in desert stream, while very long in arid, very short in desert, in snow melting system. So how to model this from that? Again, we did the same kind of assumptions, although in this case we use just a theoretical model. We want to move it from this here to this here. No armoring to armoring. And this diagram, it shows exactly the same as we see here. We use a 3 kind of layer model, as you can see, moving layer, surface layer, and subsurface layer to do the modeling. And we solve this, as you can see here. This is one of the model. And we end up in these diagrams. This is exactly the same kind of data. This is the particle size distribution, and this is the particle size in millimeters. High sediment supply flashy floods are here, which is very weakly armor or no armoring. And as we move here, as you can see, we move to a more and more armoring situation. And these are the sediment movement rates, as you can see here. So basically, theoretically, we solve it, and as I will show later on, we match what we get in the experimental work. But here again, to look on it, this is the transport rate, which indication of the supply. Here the particle size, and we see that in the armoring situation is we are somewhere here. As we increase the sediment supply, there is a major decline in the particle size till we reach. Sorry? You don't see that? I don't see anything. Okay. It doesn't matter. I'll use my hand. Okay, so it's become actually here, as you can see, well, less armored surface. So our theoretical, experimental, and field work show exactly the same kind of things, which is nice to see. And here, the solving of the model that we work on, and this is the particle size distribution of the surface. As you can see here, this is what we start from. This is this line here, and this is the develop over time. And you can see that armoring surfaces develop as a result of longer floods, while desert streams almost remain the same. We solve it theoretically, we solve it experimentally, and we saw that in the field. Okay, so the conclusion here, which is that sediment supply and hydrograph shape control the sediment transport, and that sediment supply appeared to be the most important factor in controlling sediment transport in stream, which has a lot of implication to what do we do in terms of restoring streams, and that the hydrograph play a secondary role, especially if the falling part of the hydrograph is very long. And in places like Canada, with all of these large hydrographs, really the channel develop an armor surface, which is invariant to the hydrograph or to the supply shape. So this is the kind of basic research that I do. Now I want to move on and discuss the second question. And the second question is how much sediment a fish can move. And this is a very important topic because we are trying to restore habitat. And our idea is that we take a truckload of sediment, we introduce it to the river system, and we hope for floods to mobilize a little bit the sediment, and this is the way to create the habitat. What we did not take into consideration, as you will see here, is that also fish engineer its own environment, and fish change its own environment in order to develop a more suitable habitat. And in this picture, you see all of this fish actually spawning. And this is a creek in Alaska. And you see here, as you can see, it's quite a lot of fish. And all of this surface is wavy kind of things, is dug by fish, by sockeye salmon. And they create these kind of transverse features, which we call them dunes. So the question that I came to ask here, how much sediment a fish can move? Or is it important to consider when we think about restoration issues? Again, I go back to the same diagram. This is the input to the system. These are the process. And what I am concerned now is with the salmon. How the salmon mobilize sediment, how much sediment mobilize the salmon, and what we need to do in order to take this in consideration, and if we need to change our idea in terms of restoration by taking what the salmon does to the surface into consideration. So this is just two pictures. One, a flooding in Washington, and you can see fish that due to the flooding end up in the road here. Here these are fish in the Queen Charlotte Island in British Columbia. Again, to remind that the common knowledge holds that fish excavate in order to lay eggs and so on to reproduce. And the question is how much material, and should we worry about it or not? And if it's significant in terms of landscape evolution, as I will be looking at. So what the fish does is kind of something very simple. As you can see here in this diagram, the fish lay on its side, and it starts actually hitting the surface by a really force that create a vortex, as you can see here. And this vortex end up in digging a deep kind of hole in the bed here, which in the case of sockeye can be about 20 centimeter deep. In the case of Chinook salmon, it could be larger. And with the help of the water, the sediment move a little bit and create a tail here, as you can see. And this is a real kind of pictures, as you can see. These are the reds that get excavated by the fish, and all of this river, as you can see here, dug. So what I'm going to do is to show you two kind of videos that shows the fish in action to prove that really fish mobilize a lot of sediment. These, these were taken by the University of Washington, and I got them from Alan Gutsfield. And what you see, the fish here is spawning at this place. These are Atlantic salmon. And you see the amount of fish that fish kind of mobilize. It's a lot of material that move over really about 50 or so meter area, as you can see here. Again, the same kind of fish mobilize the sediment, not lay eggs. And usually the female do the work, and the male just guard, just being the lazy in this case. And not only the sockeye, I need to get rid of this. Not only the Atlantic salmon dig, but it also the sockeye salmon also, which I'm going to talk about it a lot today, does the same thing. As you can see here, these are spawning in a little bit coarse material, and they can mobilize up to this kind of stones that you see here. And we trace them in order to see how much sediment a fish can move in comparison to a flood, and which one of them is stronger, the fish or the flood. Now you have to think about it. A river like the Fraser River in British Columbia has millions of fish returning in good years. So you can do the math in terms of the amount of material that fish can mobilize. This is a small creek, the one that I want to talk about it today, which is about 4 or 5 meters wide and get about 15,000 return every year, which is considered to be quite large for the size of the system. We did that by using certain techniques in terms of tracing sediment and measuring sediment transport. We did the study in the upper part of the Fraser Rivers. As you can see, one of the largest fish habitat in the world. As I said, millions of fish in good years return. And we looked in the upper part of the basin because we were interested in processes in small streams. And you can see this is the area that covered with sockeye. It used to be in California and so on. Almost nothing now in California, most of it in British Columbia, and the richest place actually for sockeye now is Alaska. So I will, if you want, I can elaborate why later on. So what we did, we look on the movement of sediment in real world kind of condition in the field, and we distinguish between 3 different periods in terms of a flood. This is the streamy flow in terms of a cubic meter per second, which is the volume of water, and this is the time. So we had the snow melting regime, which is here, and then we had usually floods in the summer sometimes, and the sockeye salmon spawn late in August and in September, which is during the period which have no sediment transport. So we could distinguish based on that between how much sediment a snow melting flood mobilize versus how much sediment a summer flood mobilize and how much sediment a fish can mobilize, and we compare them as you will see soon. We look first on how far away our tracers move. So we look on downstream direction, and what you see here, this is the distance of it travels in meters, and this is the year that we have data, as you can see here. The blue is the fish, and the brown kind of color is the floods. And you can see in most of the years for this case study, the fish either mobilize sediment at about the same kind of in terms of a travel distance as the floods, which means that the values are comparable, as you can see here. However, the fish is very kind of important also in vertical shifting of the sediment. As you remember, I was talking about the surface being coarse versus the subsurface being fine. So when the fish dig, it's not only shift downstream the sediment, but it also mixed between the surface and the subsurface, or in comparison to the local. And here the fish is superior to the floods. As you can see, again, the same color. The blue is the fish and the brown is the floods. In some years, the floods, especially high flows, the floods kind of mix the sediment vertically about the same. But in most years, the fish actually dig deeper and put the sediment deeper than the floods. And this has a lot of implication toward fish evolution, as I will say. I will talk about it later on. So either in terms of downstream distance, comparable kind of distance, but actually superior, the fish, in terms of vertical component. And again, this has to do with putting the eggs in a safe place, which is very important. If we look on it in terms of amount, and here tons of material, and we start looking from the mouth of the river and move upstream, because there is a preferential kind of selection of habitat. Strong and early return fish will spawn immediately in the mouth of the river, while weak fish and late spawning fish will go upstream. Upstream is the material is larger, more difficult to dig, and difficult to modify the habitat. So the the weak and the late spawning will go upstream, while the strong and the early spawning will target the lower part, which is close to the mouth. And the majority of the fish will try to target the mouth of the river. So in the mouth of the river, what you need to look here in the ratio between the fish and the flood. Here for this particular year, the fish mobilize about 50% of the floods. Here 3 times more the floods. Here more than 1, like 1.12 more than floods. Here almost twice. As we go upstream, usually the numbers decline. Again, because less fish goes upstream, and the weak fish, which doesn't dig that deep, goes upstream. So it's less, and we go upstream, as you can hear, and the fish becoming less and less effective. So most effective part in the lower part, where most of the strong, healthy, and the largest majority of the fish retain, is the place that we will have a lot of activity. And this lead to change really in the channel completely. This is another example from another creek which shows the same thing. Now if we compare in terms of a flood, and this is a simple way of looking at it, this is the ratio between fish and the flood, as you can see here. And this is the return period. You can think about it a magnitude of a floods. It's a larger floods versus smaller flood. This is a smaller floods here. These are larger floods. We look them in terms of years, how often they retain. For floods that happens yearly, as you can see here, the fish, it depends on where, if it's near the mouth of the river or upstream, can mobilize between almost very little up to 3 times more floods than the floods. As we move upstream or as we go from smaller floods to larger floods, the proportion that the fish mobilize less. So in dry years and close to the river mouth, the fish dominate the channel activity, sediment transport, channel morphology, and everything related. In years with high floods, the floods themselves dominate the system. But think about it. These floods happens every year versus these floods happens once every 5-6 years. So in overall, over thousands of years, the fish actually dictate the sediment mobility. Okay. And this is to relate to the effective female spawning. As I said, males do not do any work. So female do the digging and the spawning and so on. So we see that roughly the amount of travel distance or the depth of vertical mixing related to the number of returning fish, which has a lot of implication. Now, if I go back to the diagrams that I used before and look on the channel morphology, this is the channel morphology after floods. The brown, it means high areas in the channel, bars, as you can see here. The blue areas are low parts of the channel, which means pools or something like that, but in general. And this is the landscape that developed after the floods. And this is the landscape that developed after the fish. What the fish did, went to the freshly deposited sediment by the naval flood, as you can see here, and dug that area, which turned the bars into pools, and the pools to bars, which means that fish targeted the freshly deposited sediment for simple reason. This is with a lot of the space between the gravels, the best movement of water, a lot of oxygen go through the system, and this is what the fish needs for its habitat, a kind of nice movement of oxygen for the reproduction. So it's a completely different morphology. Okay, there are a lot of streams below dams or below lakes. So what I want to look on what happened below lakes, because a lot of lakes in British Columbia. We study all of these streams, as you can see, below lakes. And during floods, we did not find any sediment movement because the lake actually regulate the flow. No high flows because of the lake. So no sediment transport under natural conditions. But we have sediment transport. And this is sediment transport has to do with the Chinook or the large fish, as you can see here. This is the lake here. And this is looking at an aerial photo. Even you don't need to trace or to do anything. You just look on air photos, and you can identify all of these actually, as you can see here, dunes or large pile of sediment that develop as a result of fish. Without the fish, this system is dead. Nothing moves. The fish actually dictate the movement of the sediment below lakes. And this is a remarkable kind of result. And if we look in it in terms of mapping over time, this is the 1950s. I brought a few maps. These lines actually dunes that we mapped as a result of fish movement, Chinook. These actually are here and here. So you see roughly that the dunes are almost the same place, and they are in the order of 2 meters or so, which means on average, sediment move about 2 meters a year in these streams. Without the fish, this won't happen at all. Okay? Now, this is the evolutionary issue, which is amazing, because fish wants to lay eggs in a place that is protected. And if there is a sediment transport as a result of floods, then the floods will erode the bed itself, and it could actually erode or mobilize the eggs, which means that it will be bad for the reproductions. What we did here, we surveyed the location of the egg pockets in our streams, as you can see here, and we plot the vertical kind of component of the mixing of the sediment, because this is what matters. So it doesn't, we have here two kind of values, one for fish itself and one for floods. And we notice something remarkable, which means that always the fish lay eggs below the erosional layer in all years, which means there is something in the evolution of fish that tell the fish that this part of the channel is active, is not safe to lay eggs. You need to go lower than that, put the eggs there, and they will survive. And this is what you see here. In all years that we surveyed, always the fish lay eggs deeper than the floods, as you can see. Okay, so again here, no restoration program, especially those in the US that take into consideration that fish engineer its landscape. All of what we do in restoration programs is that we feed for 2-3 years sediment into the system, hoping that the fish will return, hoping the system will restore itself, and we leave it because we don't have the money, we don't have the energy in order to continue. But it's really for a healthy habitat, we need to do two things. One, we need to keep supplying with sediment because fish, as you see there, saw before, dig or excavate freshly deposit sediment because it's the most oxygenated sediment, which is needed for reproduction. And the second thing, they keep changing their landscapes. So you need to take these into consideration in order to restore habitat. And you have to choose between feeding coarse sediment to create a little bit of activity in the channel versus sand, which we are not equipped. All of the restoration kind of effort has to do with a static kind of estimate. We dump a little bit of sediment and we hope to the best results, this is why the river restoration industry in the US is one of the largest with very little outcome. So we have here is really a kind of situation that we did not tackle it. In one hand, we want to restore rivers to, as ecologists also, to restore fish habitat. On the other hand, we don't consider the activity of the fish part of the restoration. So if we don't do that, the plan is failure. Okay. Now, the third competing kind of agent, just a few conclusions here. Erosion pattern by floods, linear, versus hammock-high landscape by fish. You see the dunes there. Chinook is the only agent of sediment transport below lakes, which is very important. And fish mobilize at least the same amount of sediment like floods, if not more, especially in a dry years. The third agent is us, we human, okay? And usually we think and we teach these kind of processes as a natural processes, and we keep telling our students the natural process, what I actually was describing there, resistance, forces from water, mobilizing sediment, what sizes, what's control, and so on. But in reality, there is a major agent that we need to take it into consideration. And the diagram in front of you tell you the story. This used to be a natural landscape which went through terracing. I work a lot in China, in the middle part of the Yellow River and the Yangtze River. And if you stand in a very high area and you look around you, you see everywhere terracing, which means that there is no natural landscape in at least the case of the Yellow River and the Yangtze River, the two rivers that I work with. I will look on the Mississippi very soon. So how we human dictate the landscape that we see? In one way is by mobilizing sediment, and in the other way by developing a conservation methods to reduce the sediment transport, because again, we need to keep the soil because this is our kind of agricultural soil. And for any meter of soil that get eroded, which it takes very short time, in a few years, it takes $15,000 to $20,000 for it to develop. So the minute that we lose our soil, there is no way back. We need to wait 15 to 20,000 years. And this is actually the hockey stick curve of human history. And if we start from here by looking on the amount of material that a human move, for building, for mining, for whatever, okay, per capita. And look in history, don't pay attention to the color. This is just to emphasize certain things. They are not really correct in terms of timing. And we start with the Egyptian, ancient Egyptian at the time. They used to mobilize a lot of sediment to build temples, to build the pyramids, and so on. So early in human history, the Egyptians actually mobilized most sediment on Earth. The second period has to do with Rome and building roads to service the empire. Rome built a lot of roads, built a lot of temples, and this ended up in increasing a little bit the amount of mobilized sediment due to human activity in comparison to ancient Egypt. Then we reach London and the Renaissance period, 15th century and so on, the coal mining, the roads, and all of this to service the empire end up in mobilizing a lot of sediment. And what you see here now is that the country that mobilized the most sediment on Earth is the US, with all of the building of that goes on in the US. And if you take away the US and calculate for the rest of the world here, which is a slight increase from the period of the mining in London and so on. But as you can see, the US generate most of sediment. I would say now actually there is another competitor with the US in terms of generating sediment. This is the province of Alberta in British Columbia with the sand tars and so on. It's actually the most producer of sediment now per capita probably in Alberta, or it will be close to the US as you can see here. So you can see that this curve is actually shaped the human history. What I'm going to show you that it's not only in the case of building and so on, it has to do with other things as we see if we look on the history of China. So the first place here to look on it in the Luce Plateau and the Yellow River in China. The sources of water in the upper part in Tibet, as you can see. Most of the sediment comes from this here. This is the most erodible landscape on Earth. The highest amount of sediment now move on land on Earth, it comes from here. Until about the 1950s and so on, the Yellow River used to supply about 6% of the global ocean sediment budget. 6%. That's a huge amount of sediment, okay? And it used to deposit a lot of sediment, as you can see here in the northern plain of China. What we did here, we look on a spatial pattern of sediment along the basin to look on where the sediment comes from, what amount of sediment, and how the conservation method affect that. This is the landscape that used to be roughly when the Mughals entered to China, destroyed all of the irrigation canal and destroyed agriculture and converted the landscape to a kind of a grass landscape for their horses and so on, which led to a major decline in agricultural activities in China. This is roughly in the 1950s, as you can see line. And this is about the erosional rate that happened in less than 50 years. It's a huge amount of erosion for this landscape. So you look here versus here, and you can do a little bit of calculation. And all of this landscape went through major erosional processes. And most of it has to do with the human activities. And this is the landscape that we see. All of these terraces were actually built during the Cultural Revolution when Mao Zedong ordered people to go back to farm the lands and so on. So they built terraces and they built check dams. And these dams, as you can see here, you use them now as agricultural lands. Now these terraces actually in deteriorating, but China building a lot of these terraces. A lot, it means everywhere. Everywhere you look, they are building new terraces. The difference is that these were built by cheap labor, humans. Now they use heavy machinery in order to build that. And this is the shift in China. This is a very large Wadgunhe River. It's a quite large river basin. And you see till the 1970s roughly, or something like that, almost no change in the land use. The terraced area versus the check dams or the grassland or the forestation and so on. And immediately after the 1970, a huge change on the landscape. The Chinese government decided to reduce erosional rates in the landscape because they were afraid that they were losing their agricultural land. So they started the most massive soil conservation kind of program in at least in the recent times. And this has led to a major change in the land use. And this is what you see. You drive for kilometers everywhere. They are planting trees in order to tackle soil erosion and the movement of sand. This is sand, wind sand driven that keep moving from the Gobi Desert to this area here. So our model, and these are the results of working along the Yellow River, which is the most kind of rich data set that we ever get. And what we did, we create a spatial map in order, one, to predict where the sediment comes from. Because if you want to target soil conservation, you need to know where the sediment comes from. And you need to know how much sediment. And you need to test how effective your conservation methods. So if we look on this map here, this is map that we produced based on our work. It's 1 kilometer kind of a scale. We call it KS, is 1 kilometer scale. And this is another map that we generate, which is about 1,000 square kilometers. There are different things to see in these maps. But what you see here, this is the heavy agricultural land in China, and you see a lot of erosional rate. It's more than 100,000 tons per square kilometer per year. It's really amazing amount. It's kind of all of the landscape disappearing as you look at it in terms of these things. So this is a high kind of area of sediment transport. This is high area. There is another high area here. And this is very important. There is a scale issue here that you need to think about it, which is 1 square kilometer. Now, if I compare this to this, this is before they implemented soil conservation method, and this is after. This is more than 100,000 tons per square kilometer per year. This is less than 30. So they managed to reduce the amount of erosion significantly in the landscape and to keep the sediment in the landscape. However, they created a major problem in another place. If you look on this map here, you see a completely different picture than there. What you see here is that the color become kind of heavier as you go downstream from this area to this area. This is yellow, almost no sediment. As you can see, this is heavy here. But what you see here, it's becoming heavier, heavier, heavier as you go that way, which means that as you go downstream, you increase the sediment transport rate significantly. So they kept the sediment in the hill slopes in the fields, but they created a major problems along the valleys and along the rivers, which is exactly what happened with the Mississippi rivers 100 years ago, which they related to more than 100 years ago. So it's effective. It target the slopes, but it forget the rivers, and they have a major depositional problem in this area that need to deal with it. So if you look on it in terms of things here, as you remember, I said 6% of the world global flux of sediment into ocean came from the Yellow River. Here, this is the kind of historical rate, 0.4 kind of 10 to the power 9 tons. It's increased during the agricultural period to 1, declined during the invasion of the Mongols to about 0.6, increased to about 1.2 during Mao Zedong period. And immediately after the Cultural Revolution, the terracing, it declined to 0.4, and now it's below the natural process. This is what creates a lot of deposition and major problems for them along the plain of China, along the northern plain of China, which is very important here. And again, the decline here has to do with converting the land from agriculture to grass to feed the horses of the Mughal invader into China. And again here, these are completely different data sets, as you can see here, because we are looking on depositional rate along the plains of China versus years. This is the historical records, as you can see, very little deposition, which means in the plains, which means very little sediment leave the river system. This is during accelerated a little bit of erosion during the climate shift and so on. And this is accelerated during human activity. This is early kind of history of modern China in the 1950s and so on. It reached kind of very high values around the 1970s, and this is now below the natural kind of thing. So they went to the extreme, but again, as I said, they created problems in another place. If you want to look on another example, this is the Yangtze River and the Three Gorges Dam, actually in the news most of the time. What we did here, we did the same, but we looked on reach scale kind of sediment balance between these different reaches. So what I want to show you results from this part here, this reach, Pingshan and Jitu here, and Jitu and Yishang. And the dams that they built here, this is the first one, which was a small kind of dam. And then they built the Three Gorges Dam on the river here. And it has a lot of implication, not only for sediment, but it also for the flow of the river into the China Sea. This is the sediment kind of balance, if you want to think about it. Input, output, the yellow indicate erosion, and the blue indicate deposition. And you can see this is kind of the values before the building of the first dam. The first dam was a little bit small, kind of small. It caused a little bit of decline in the sediment, but not that major. But the building of the Three Gorges Dam transferred the whole reach from kind of erosional, as you can see, mostly yellow, into blue, which is depositional, which means that it created a completely different system, as you can see here. The other reach, which is downstream, used to have more kind of depositional situation. The building of the Three Gorges Dam not only reduced the amount of sediment significantly, but to create a new reality, completely transfer the landscape. And here the history of China, the modern history of China, how it's related to sediment. If you look on it, it started from the period of land accumulation, which is immediately after Mao Zedong came to power, the Great Leap, and then the Cultural Revolution. And then Deng Xiaoping here declared that China is open for business and so on, until we have kind of somewhere here the conservation and so on. What we see here, what we call a departure kind of a plot. This is the sediment, and what we need to look on it, it's a change in the trend. We don't know when the trend started, but what this trend here changed somewhere here, and from this point here we have actually decline in the movement of the sediment in comparison to this here, which means we consider this is a major change in the landscape. As you can see, it's almost 30-year change. Here roughly we had a very large events on the Yangtze River, and then followed by the closure of the Three Gorges Dam. This is one period which is associated with the Cultural Revolution, which has led to major change in the landscape during sending people for education and so on. The larger flood and the Three Gorges Dam started a new era in terms of that landscape. So you can see a clear link between humans and landscapes, and it's actually they are competing in shaping the landscapes. And this is what happens if we look on the period before the building of the Three Gorges Dam. This is the relation between input and output in our kind of reach sediment balance, which is roughly a unity kind of thing in terms of way. And this is the data that we actually analyze after the Three Gorges Dam. It's well below whatever considered to be natural, which is mean it's a completely different system. It's not anymore the river that we think about it. Now come to the US. This is a work in progress, and what you see here, it's a map of the Mississippi River. Now the US has at least 80,000 large dams. 80,000. It's probably per capita the largest numbers of dams, large dams in the world. 80,000. What we are dealing with a huge data set, and we were very surprised that there is no a single agency that deal with the data. So we work closely with the Geological Survey in order to develop a model for the Mississippi River, and it's quite challenging, but we are really moving ahead with it. We are looking on the Missouri River with all of the changes because it's very important. It's a grassland versus the other part of the basin. And we already analyzed close to 1,000 dams, which is the largest kind of data set worldwide in terms of values. But also we analyzed data from the Geological Survey collected from the US, about 5,000, but 3,000 or roughly like this number within the Mississippi Basin. And we went back in terms of land use to 1900 until today. And we actually looked on the changes in the land use. As you can see here, this is the 1900 croplands versus grassland, as you can see here. And this is the Missouri rivers with all of the grassland, which has a lot of kind of a question now about the operation of the dams, that basin. And you can see roughly it's the same area. There is a little bit shift. This is 2000. In terms of croplands, we have some changes of the kind of crops, but in general, this is the belt of agricultural land. Here we work on nutrition, we work on soil quality, sediment transport. It's a very large project that quite few people involved in it. But this is the kind of thing that we are looking in the history of the basin. And we have actually human geographers work on how the landscape changed in terms of history. So this is what we are doing, which is in the middle of our work. We hope in a half year or less to finish this work, which will be kind of amazing because it's the largest in its kind in the world. So let's summarize here. And this kind of table summarizes everything. The principal surface builders of the globe or the landscapes are mountain building and volcanic kind of eruptions. Volcanic eruption, tectonics are the principal process that build landscape on Earth. And if we put them together, they generate about 44 billion tons of material a year. Now, if we look on rivers, which control the landscape, as you can see here, they generate about 53. So roughly, given the way that we estimate these things, I do not see that much difference between 53 and 44. These are kind of rough estimate, but they are a good estimate. And if we look about us, a human, we generate about 45. So in general, 1/3 of the sediment that mobilize over the globe is related to mountain building volcanic eruptions, 1/3 because of rivers, and 1/3 because of us as a humans, which is really amazing, which means that we need to think about the globe in a completely different way. And this is the kind of conclusion that I would come, that soil conservation method works in the hill slopes and the field scale, and this is what we saw in the Mississippi. In the hill slopes, the sediment remain immediately after the 1930s and the implementation of the conservation. But it creates a lot of erosional processes along the valleys, which means that the question where you put your money, you put a lot of money in conserving field, but you have to spend a lot of money also to keep the valleys because you cannot afford to leave. Most of the sediment actually come from bank erosion and flood plains, and dams, land conservation practices reduce the flux of sediment to the ocean completely. And it's time to welcome you to a new geological time, which is the Anthropocene. And thank you. This is my friend Gary Barker. We work quite a lot from Urbana on modeling, and these are other people who help, and a lot of students that I did not have a space to mention all of them. Thank you.
Thank you very much. That was a very interesting talk. We have time for some questions, if anyone would like to ask Dr. Hassan.
Yes. About 20 years ago, I built a system that simulated underwater sound. It was three-dimensional simulation and included waste, transverse waste in the sediment. As part of that, I needed to find out what the characteristics of the sediment were. So I found tables that gave characteristics of sediment from all around the world. And then I proceeded to go practice analysis of that data and found there was a perfect anti-correlation between sediment density and porosity. I did not expect that. I expected there would be some component due to the composition of the sediment, but there was none. And I was at a loss to explain that. Can you tell me why sediments from all around the world would have this same relation between density and porosity, no concern for, no regard for what the components of the composition of the sediment was?
It's actually the porosity is related to particle size, and it's related to the like the sorting of the material. It's usually, it has very little to do with the density of the material. It has to do mostly with the particle size distribution and how the particle size is distributed in a poorly sorted sediment, which means that you have a wide range of particle sizes. You will expect to find a small porosity. And in a well-sorted sediment, so if you deal with well-sorted sediment, you will end up with about 30–40% roughly, because this is the kind of backing that you have in the system. So this is what I think is happening.
So the density doesn't depend on the composition?
No, no. It's sometimes you will have a little bit of sorting because of density, but in most of sediment, if we are well mixed and poorly sorted, then you won't find that, at least in the sediment that I deal with. No.
The number of dams you found is staggering. But I have also observed that we create situations in riverbeds, and in particular I was looking at where we put roadbeds across river valleys, mostly with fill, and we only bridge in town. But when the river floods, the upstream side acts like a dam, the downstream side does not. So you end up with deposition
Yeah.
of finer sediments on the upstream side and erosion and coarser sediments on the downstream side. And there's a lot more road crossing of rivers than there are dams.
That's true, but you have to look on the major players. So if you think about it in terms of sediment, that if you put a barrier, as you describe, then what you create a step in the river system, which is mostly will dissipate energy in the system, but after a while it's become part of the river. And this is what happened in most part of the, in the eastern part of the US. The early European settlers, they built a lot of small kind of these things. And if you go now to these rivers, they are part of the system. If you don't know the history of that landscape, you will be kind of thinking what happened, why there is a step, which has to do with the human activity. This is why actually we took a human geography students to go through the archive in the US and to read it through us and to see what happens, so we won't misinterpret something. But it become part of the river. What matters when you think about large dams, these large dams, they kind of trap a lot of sediment. And the Mississippi River used to transfer a huge amount of sediment. Now it's about 10% or 20% of what used to be 200, 300 years ago. And this has a lot of implication to the delta and so on. So these small things, after a while, they don't matter. And it's exactly what you see in the case of the Yangtze River. They built two different dams, one small and one large. The small has a very little impact. The Three Gorges Dam just killed the system. The same in the case of Egypt. I started with Egypt, and I said Egypt used to benefit from a flooding with all of the mud and so on, which needed for the agriculture. The minute that they built the dam, they secure the water resources for Egypt because of the dam. But on the other hand, they created a measure of problems, which has to do with degradation and so on. So the question, like you build a dam in one side to get certain things, but you create a problem in the other side. And this is exactly what happened. And this is why people talk about Egypt civilization survives all these years because of the flooding of the Nile. There are many different ways. There is no acceptable way. It depends on the size of the system. If the river is very small, then what we do, we kind of put a box in the bed with a load cell or a pressure transducer or whatever, and we measure the accumulation of sediment. If the river system is large, then we lower something from a boat, a sampler, that collects sediment, and we estimate it. There are some correction factors. This is what we do with the coarse material. With the fine material, we use turbidity, or we use bottles. In the old days, we used to use bottles, but we use bottles in order to calibrate the turbidity and so on. Or, in the case of the Mississippi, we use also the dams. They survey the dams for us, so we use their data in order to estimate the sediment. So there are many different ways to do that. We use tracers. This is the kind of thing that I showed. We put stones with radio tracers in them, so when the fish hit them, they move, and with the radio we can find them.
I thought about the effect of the salmon in there, and it looks like it somehow or another the salmon know how far you've got to go to put the eggs what we want, or what is that?
Well, this is what surprised us, how the salmon knows how deep to dig. And they dig. Well, there are differences because not all salmon the same. Pink salmon usually lay a lot of eggs everywhere. So about 95% of the eggs, they don't survive. So they lay a lot of eggs in order for a few to survive. The sockeye salmon is very selective. Most of the eggs survives, and the result that I showed from the sockeye salmon, it seems to me that when you think about the movement of water through the grains, if it's a fresh sediment, then the movement of water quite fast for simple reason because there is no small fine grains that block the space in between them. So water and oxygen move through the system. Below that, actually, it's less movement of water and oxygen. It seems that some way the fish sense that and put the eggs there. I don't know. I think about it just an evolutionary kind of thing that the fish adapt for survival. I don't know. I'm not a biologist.
You make the statement that the weaker salmon swim further upriver.
Yes.
That sort of sounds counterintuitive. That the stronger salmon should be the ones that have the stamina to go further upriver.
Well, I'm not sure about that because in life for a human also it doesn't mean the stronger will work harder than the weak or the rich more than the... I think it's a matter of fighting on space. When the fish comes, the weak ones, they cannot actually dig because they get chased by the strong ones. The strong ones goes to the easy places to dig, and they occupy these places. The minute that the weak one comes, they chase them out, and they have to go upstream. So usually, downstream, all of the area dug, and if you look on a turbidity concentration, and I did not show the result, but we have some results, and you see exactly the time that they start spawning, it's the amount of fine sediment in the system increase. And as you go upstream, you see less. You see the characteristics of the reeds that they build in terms of size, and the number declined significantly. And you look on the type of fish because we work with fisheries and they quote fish and they survey them. Usually the weak ones, the small ones goes up. The ones that cannot actually protect their territory or occupy territory down. But usually in general, less fish goes upstream because it's easier to dig downstream, smaller grains.
I have one quick question. How long will it take before the sediment fills in the area in front of the Three Gorges Dam? Is that a long period, do you estimate, or?
Well, it's the question it should be, it's what sort of environmental consequences will be in the lower part, because it will take a lot of time. The place that they built it, the Three Gorges Dam has been in planning for at least 30 years. And they planned it, but they did not build it for a simple reason. The military in China wanted to build it in a certain place. The scientists said this is a bad place to build it because it's a place with a lot of sediment, it will fill it quite fast, and it's not worth it. The military said, no, this is the place that we can protect it. If there is a war and somebody actually attack that place, it could lead to catastrophe in China. So the military resisted building the dam in its place. The scientists said, no way to build it there because it's really kind of lost. And lately the scientists prevailed, and this is why they built it at that place. So there is very little sediment that actually reached that place. But the problem is that the reduction in the flow downstream, which reduced significantly the ability to mobilize sediment, and this is a change. So the dam will take quite a lot of times, probably a few good 100 years to build, like the dams in the Mississippi and so on. Usually the engineers, when they design these dams, they take a kind of safety factor, which is 2 or 3 times or something like that. The problem is that the environmental consequences, and if it's worth it, one of the issues that is going on in the US at the moment is that they are decommissioning a lot of dams. So in the US, they build a lot of dams with no knowledge. And now they are decommissioning dams with no knowledge. And what they don't tell you, that most of the dams that they are decommissioning, they are small and has no economic value, and they cost more than they're worth it. There is a dam in California, actually, and there is a huge argument. It was built in the 1940s to supply water for irrigation for 500-600 years. It got filled by the 1960s. And there is now an argument what to do with that dam. It's full of sediment. If they open it in a way, they will flood the town downstream. They don't want to do that. So if they actually decide to track the sediment, just to fill trucks with sediment, and to dump the sediment somewhere, it doesn't matter where, just to carry it, it will, and if they can fill every 10 seconds a truck, it will take them 11 years to evacuate the sediment, and between $300 to $500 million. Well, the benefit of that dam, it wasn't $300-400 million. So it's quite a huge dilemma. It's the same in China, the same in India. We built all of these dams with no knowledge. Now we are decommissioning them with no knowledge, and we are in a trap. We put a lot of money on these issues without thinking. The same with the river restoration. It's a huge programs in the US, but you see, they don't actually consider the fish at all.
This would make 1 or 2 more questions.
You slide on the snow melt, and of course, we're approaching what I consider to be almost a snowless winter. And of course, if you've got the snow melt, you got the least amount of erosion. In other words, it looks like the global heating, if you want to call that. In other words, this is the warmest winter, if you want to call that, since 1950 in Washington, D.C. area.
Yeah, well,
Does that impact the
it's not true that snow melt doesn't create floods. We have a lot of floods because of snow melting. But in general, if you think about it, flash floods or deserts, when we have a concentrated water, it will create larger floods. But also you have to think about it in terms of frequency. These floods happen once every quite a few years, but the snow melting events happens all of the time. Now, if the ice melt and there is a shift in the snow due to climate shift and so on, then these places that used to have a lot of snow melting, they will have either a combination of snow and rain, which will create larger floods, or they will shift to a more rain-driven floods, which will be more erosional processes, and it will change the whole river system. Yes.
Last question.
Yes, I've heard that the huge number of dams in the United States has changed the also what you described in terms of having a longer tail on this, leading to a more stable structure, sounds like annealing to me. Basically how simulated annealing finds a global maximum.
Yeah.
It seems to be the same process.
I don't know the first one. I never heard about that in terms of it changing. So I cannot comment on that.
Okay, I'm sure Dr. Hassan will take some more questions during the social hour.